Okay, welcome everybody. My name is Maciej and I'm a standards developer at ABYC. I'm former or still marine technician and former sailing instructor, charter captain. And now I work for the ABYC, working with the electrical committee on the electrical standards. And the topic of today's presentation will be lithium-ion batteries. As we all know, it's a hot topic these days and everybody is interested. So I'll try to do like a quick overview of the technology, applicable standards, and all the testing that we did for lithium-ion batteries. So, okay, so let's see if I can, okay. So just shortly, what ABYC is. We are a non-profit organization that we develop the voluntary safety standards for the marine industry, for the boat builders, technicians, surveyors. We also provide educational resources. So I encourage everybody to visit our website. There are a lot of resources, not only for the technicians, but we have a lot of like free and low-cost courses on our online platform, and you can also check our YouTube channel. We have a few interesting videos there, including one on lithium-ion batteries as well. There are several member benefits. I don't know if any of you are ABYC members, but we are always happy to answer any questions. And even if you are not a member, you're always welcome to reach out to me, and I'll be happy to help you with any technical questions that you might have. So what we are going to talk about today, shortly address how the lithium-ion batteries work, what's the basic terminology here, what are different chemistries of lithium-ion batteries, and the lithium-ion, why the chemistry matters, because we say lithium-ion battery, but it's actually more than just one type of lithium-ion battery. And we will address all the safety concerns and are they safe to install on the boat or not, or do they present any safety hazards? So we will address that. Okay, so let's take a look at the screen here. And so as most the batteries will have the cathode and the anode, and like with lead acid batteries, they'll work as reversible chemical reaction. So what we'll have on the cathode side right here, it's usually lithium salt or lithium oxide. For example, it can be lithium cobalt oxide or lithium iron phosphate. That's what we refer to the chemistry is the cathode material. And we have the positive lithium ions floating in the organic electrolyte plastic separator, and the anode, which is usually composed of carbon. And what happens during the charging phase, the electrons are pumped from the anode to the cathode, and at the same time the lithium ions, they penetrate the separator and go from the cathode to the anode. And what's important here, that the electrons never actually bind with the lithium ions. So we never form lithium metal in these lithium-ion batteries. So that's what is the difference between the lithium-ion batteries and lithium metal batteries, which are not rechargeable, and we're not talking about them today. So there are basic 6 lithium-ion battery chemistries, and what you can see on the boat, you usually see lithium iron phosphate battery, and I often hear, okay, lithium iron phosphate, but that many people will say that's not lithium ion battery, but in fact it is. It's just one of the 6 types of lithium ion battery. The lithium iron phosphate is that material that creates the cathode inside the battery. The other type is lithium nickel manganese cobalt oxide that can be found on boats using electric propulsion, especially on those systems that were adapted from the automotive systems, especially operating on high voltage levels. For example, Torqeedo's high voltage electric propulsion systems, they will use the NMC battery. But what you usually see on the cruising boat, for example, on the like a house bank, that will be lithium iron phosphate battery. Other types are used, for example, each lithium cobalt oxide can be used in portable electronics and power tools. Lithium manganese oxide, that's something that used to be used in, I think, Nissan Leaf and other electric cars. Lithium nickel cobalt aluminum oxide was used in Teslas, and actually now a lot of Tesla cars are switching to lithium iron phosphate. They have a little bit lower energy density, but they are more stable when it comes to thermal stability, so they are safer. And finally, we have all kind of lithium iron phosphate batteries, and they can be drop-in batteries, or they can be the custom built systems with external BMSs. So let's go quickly through some battery terminology. So we have battery cell, that's the basic building block of the battery. And unlike lead acid batteries, where you have 6 cells, here in typical 12-volt lithium ion battery, you will have 4 cells, and they'll create your nominal 12-volt battery. So then we have, of course, the battery bank, when you have multiple batteries connected, and the whole battery system with all the components like BMS, battery management system, and switches. So the other thing to remember is, and the important term here is the safe operating envelope. What that is, it's a set of limits that's set by the battery manufacturer. For example, that would be high voltage limit and low voltage limit, high temperature limit, and low temperature limit. And that's the set of limits within the battery supposed to operate. And if you go outside of these limits, what happens, there is a battery management system that will shut down, that will disconnect the battery from the rest of the electrical system to protect the battery and protect the boat. We also often talk about drop-in batteries. They are like your typical group 24, 27 batteries, and they will contain the BMS inside the battery case. I mean, inside that plastic box. But what is inside really is 4 cells or multiple cylindrical cells, depending on how the battery is built inside, the BMS, and the cell balancing system. So there are multiple electronics actually inside that plastic box. So it's a little bit different than lead acid battery. However, from the outside, it looks very similar. So let's look at the main differences between the lead acid battery and the lithium ion battery. So the main differences will come to the energy density, the lifespan, the venting, charging time, and the voltage curve and the Peucard effect. So let's review all these differences here. So what's the energy density? So basically it's how much energy you have per pound or per kilogram. So how many watt hours or amp hours you would have per unit of weight. So let's say your typical 100 amp hour battery would weigh three times as much as when you have lead acid battery when you compare to lithium iron phosphate, for example. And as you can see, these different chemistries will have different energy density. So that's your LFP battery right here. So that's your typical boat lithium ion battery. It's somewhere in the middle. It's not as high as some of other chemistries, but as we'll see in a moment, there are also other differences because the thermal stability between these chemistries also varies. And why the thermal stability is important, we'll shortly talk about that when it comes to the thermal runaway and all the fire hazards. So basically, what it comes to is the temperature at which the cathode will decompose and shed the oxygen, and that oxygen will fuel the chemical reaction and the fire, making that self-propagating very difficult to stop chemical reaction. And with lithium iron phosphate batteries, that temperature is very high. It's 350 Celsius. So that's even higher comparing to what you can get. You can put your battery in the oven and it won't run into the thermal runaway because it won't reach 350 C. So it's very difficult to reach that high temperature. With other chemistries like lithium iron or like lithium cobalt oxide, that temperature is much lower. So the cathode will decompose at much lower temperature, which potentially can lead to the thermal runaway. And the lifespan. Of course, the lifespan, it depends on many different factors. Every battery can be abused and killed prematurely, but assuming we'll follow the manufacturer's recommendations from the lead acid battery, you can get a few hundred cycles, while from the lithium iron phosphate battery you can get between 3,000 and 5,000 cycles. So it's pretty dramatic difference when it comes to the lifespan. And I know people who have these batteries on their boats for over 10 years, and they are still, going strong and keeping the charge. And it has been like, from what I heard, a few thousand cycles. Still, there is no reason to replace them. So there is pretty dramatic difference when it comes to the lifespan between the traditional lead acid battery and lithium iron phosphate. The other difference between the lead acid and the lithium iron phosphate is how they behave when they're being discharged. So normally when you discharge, you can see that that blue curve here. When you discharge your lead acid batteries, the more you discharge the battery, the more the voltage will drop and become lower and lower. With the lithium ion battery, the voltage curve is pretty flat till the battery is almost all completely discharged. And when you see the voltage dip, that means that the battery is pretty much done. And that's also important when it comes to certain equipment that's voltage sensitive, and you don't have any problems with the voltage dip. When it comes to the charging, the lithium ion batteries, comparing to lead acid batteries, they have very low internal resistance, so they'll accept the very high rate of charge. So most of, as you can see on the black curve here, most of the charging will happen in bulk. So you can see that rapid, raise in voltage here, and at that point the charging is pretty much done. And that low resistance has its own advantage, the fast charging time, but it also can be problematic sometimes when it comes, for example, to using alternator when you charge your lithium-ion batteries, because if it's not installed properly, for the lithium-ion battery, you could technically overheat the alternator because it will draw so much current from it, especially in low RPMs, when the cooling fan is not spinning fast enough to cool down the device. Okay, so now we have the Peucart effect. So basically, as the rate of discharge increases, the battery available capacity decreases. So your typical 100 amp hour battery might be rated for 100 amp hours at, let's say, 5 amp load. But when you try to draw like 50 amps from the same battery, the capacity will be much lower. And we can see that on these red curves here. However, also because of the low internal resistance of the lithium-ion battery, it's not really affected by the Peucart effect. So you can maintain your capacity and still use for very large loads. That's why lithium-ion batteries are more suitable for higher loads. So we can see them used all the time for the electric propulsion, for example. And now we can talk a little bit about problems and what we can, what can go wrong. So we're talking about safe operating envelope before, and so the main causes for the lithium-ion battery failures are high voltage, so overcharging, and low voltage, over discharging. I won't go to technical details here. What basically happens there is you have your lithium ions binding with the electrons. If you have too many electrons, when you overcharge the battery, you form the lithium metal inside the battery. So that's something that's not supposed to happen. And then that lithium metal can penetrate the separator and cause internal short. And to prevent that, we have the BMS that will disconnect the battery when it reaches certain level of voltage or temperature. Cell failure can be another problem. So using low quality cells with some impurities, and that's why using the quality cells is very important. And in our new lithium-ion battery standard, we actually require that these cells will meet the certain testing criteria. Of course, external damage can cause some problems here. If somebody puts a nail through the battery, which we will see in a few minutes, that can create internal short and kill the battery or cause the fire in some chemistries. And also water ingress. If the water gets inside the cell, it can also create the short inside. And probably heard about the cases that after the Hurricane Ian, that if you submerge electric cars, they burst in flames after a few days. I don't know exactly what the cause of the fire was, and if there was an investigation, but that's what we heard. And that's why we require also that if the certain IP ratings, if the battery is exposed to the water. So let's talk about the F word, fire. Are they safe? So we probably all heard about the fires of lithium. That's the Tesla that's on fire here, and I think that's the battery that from the famous Boeing Dreamliner. Neither of them is lithium iron phosphate. They use different chemistries that were much less stable. So that's the good news. We usually don't use these batteries on boats. So what's the thermal runaway? It's basically the self-propagating chemical reaction that's very hard to stop when it starts. And how it happens. So that's what we were talking before about. So we have some, we have some external faults. For example, high temperature, fire, external fire, or some, the area when the temperature is very high, or we have mechanical damage, we have overcharging, over discharging. So what happens, the separator will start melting between the anode and the cathode, and that will create the internal short inside the battery. And if the thermal stability of the cathode is very low, like in lithium cobalt oxide, the cathode will decompose and shed the oxygen that will fuel that chemical reaction. In case of lithium iron phosphate battery, that temperature required to decompose the cathode is very high. So it's very difficult to drive these things into the thermal runaway, and I tried. I'll show you a few pictures in a while what we did. We abuse scenarios, what can go wrong, and I wasn't able to create any flames. So yes, we did some. The Coast Guard asked us to do some battery testing on lithium iron phosphate. So and I'll just show you a few pictures here. We did multiple tests and repeated these tests, multiple fault scenarios. For example, here you can see the 4 cells connected in a 12-volt battery with some large cables, and we were trying to overcharge and over discharge these cells. You can see the thermocouples going to the battery. We're checking the temperature. We had the temp sensor, the battery monitor there. And all I was able to achieve was basically create the damage to the battery. And I just said these cells, they didn't have any BMS and no battery management system, no protective circuits. They were just 4 bare cells, so connected into the 12-volt battery. So for example, what I did, I overcharged the 12-volt battery with like 30-volt power supply. Again, nothing really happened. I discharged it almost to the 0 and then rapidly recharged. And again, all I was able to achieve was to damage the battery, damage the cells, a little bit external swelling and leakage of the electrolyte. The temperature raise in this test, I wasn't able to get anywhere near 100 C. So it's way below, the thermal runaway threshold. Here we're doing some submersion tests. So, and again, we ran into the different scenarios. We did salt water, fresh water, with load, without the load. So basically, the worst thing that we could do to the battery was destroy that with the stray current. There was no temperature raise, no after any problems after the battery was removed from the water, and the fastest damage was done to the battery that was not connected to the load and submerged in the salt water. It's probably because all the energy that was stored in the battery was directed to, it was used to destroy the metals that were contained in the battery. When the battery that was connected to the load was discharged faster, so there was not enough energy left but again, all I was able to do was to destroy these cells and destroy the battery. Another test we did, that talking about the nails, we put some nails in the cell, and that actually raised the temperature to like we have 220 Fahrenheit, like 110, 120 C. Again, not very high. We did multiple tests with nails, and let's see, got a short video here. Maybe I'll put it on higher speed. So basically, the cell was nailed down with a couple of framing nails, and then we can see what happens. We have some electrolyte leakage here. Of course, when you put the nail through the cell, it will create the short circuit. The temperature raise is around 110, 120 C. So I can expect that I would have the temperature raised as well when I put the nail through the lead acid battery or to large battery cables. And that lasted about a minute, and then it stopped. So the electrolyte didn't catch on fire. The piece of wood underneath didn't catch on fire. So at that point, I kind of ran out of ideas what else I can do to to destroy these things other than putting them in the fire. So that's another thing that we did. So we did some fire tests, as you can see on both here. And let's see another slide. And what we did, we put the lithium-ion battery that was pretty large, like 200 amp hour, the battery inside the boat. And that's the picture before the fire. That's the picture after fire. The battery is still there. I mean, it looks a little bit burned and smoke. But interesting thing is here, that's the gas tank that was there. That was almost empty. It had just had some fumes there, and that thing exploded. And we actually got pretty excited for a while because we thought, okay, we see the explosion here the battery. Oh, I hear some bells. So I don't know. Is my time over? Anyway, you can see the battery is still here. And interesting thing is, even if it looked like that, it's still showing like 5 volts after they put down the fire. So there was still some electrolyte left inside. There are multiple batteries that we put in the fire in a few boats. And that's the video that we got pretty excited that something happened. Yeah, so that piece of that blew up was the cockpit cell on that boat. And first we thought that was battery, but no, that was the gas tank that still contained some fumes and explosion. All right. Okay, so that's all the tests that we did. I mean, not all the tests, but a few tests that we did. You know, to see what can go wrong with lithium-ion batteries, and especially we focused here on lithium iron phosphate batteries because that's the chemistry that's used on 90% of the boats, not counting some high voltage propulsion systems that used MNC chemistry. And so far I was able only to create damage to the cells themselves, and I couldn't see any flames, unfortunately or fortunately. Okay, so let's see. So we have let's do I want to do like a short overview of the lithium-ion battery standard, because we actually last year in 2022 we published for the first time our E13 lithium-ion battery standard. In the past we had TE13, which was a technical information report on lithium-ion batteries, but that document was taken by the electrical committee and developed into the standard. So now we have a document that addresses actually battery selection, installation, system design, and all the safety information there. So what's there? I mean, that's the boring part, but just a few slides. We put a lot of emphasis on following manufacturers' recommendations because all batteries are different, all systems are different, and sometimes you have prismatic cells or you have cylindrical cells. They are different. They have internal BMS or external BMS. It's also different. So basically follow manufacturers' recommendations when it comes to many of these factors. And water break. And as I mentioned before, the quality of the cell is important because you can have very poor quality cells, and they are available. People buy them from all these Alibaba and AliExpress, Chinese places, and there are good cells and bad cells. So what we actually put the requirement in the standard is very minimum requirement, but that the batteries or cells shall meet the testing requirements of at least one of the following standards. So it's their IEC or UL standards. And actually RV industry, they already require that. So a lot of battery manufacturers already comply with that requirement. Yeah, the other thing is that the battery location, ambient temperature, that's what we mentioned before. You don't want to put your batteries close to the heat sources, like close to the deck in the hot Florida sun, or close to the engine room, or inside the engine room. Even if it won't hurt the battery, it might decrease the lifespan of the battery. And also, if it reaches the point, when the BMS will disconnect the battery, and it will reach the shutdown point, you will be without the battery. So, so that's not a good scenario either. So just avoid, installing the batteries close to the external heat sources. Of course, the BMS will disconnect the battery and protect the battery or the boat from the damage, but also being without the battery is not the good thing. Shock and vibration is another concern. As we know, the lithium-ion batteries are a little bit different. The lead acid batteries, they contain some internal circuits. And as we know, all the electronics, they don't like multiple cycles of slamming on waves and vibration that all that we can see on boats. So that our traditional requirement was no more than 1 inch of movement in each each way. But we decided that it might be a little bit too much for the lithium-ion batteries, especially for those that are connected with rigid bars, because you can also, if they're connected with rigid bars, not the flexible jumpers, you can also damage the battery terminals. So if there are no other battery manufacturer recommendations, we require that the batteries are restrained to prevent any visible movement. We cannot say that they won't move at all, because there will be always some movement, but no visible movement. And that's how most of these lithium-ion batteries on boats are installed these days. Water ingress. So that's what we mentioned before. So we used our, weatherproof and watertight ratings that we use in other standards. So basically it's either IP54 or IP67, depends if it's location exposed to rain, spray, or splash, or exposed to the flooding and submersion. Most of the batteries that are on the market today are built to IP67 standard, and to protect against the water ingress. And all the electrical requirements. So first, BMS, overcurrent protection, switches, disconnector, charging sources, and battery banks. That's all you can find in E13 standard. So let's start from the BMS. As we said, it's the battery management system that's intended to disconnect the battery from the system when it reaches one of the limits, either high voltage, low voltage, high temperature, low temperature limit. That's the basic functions of the BMS. And that can be either internal, like in case of these drop-in batteries, it's inside that plastic box, or it can be external. The Victron is a good example of the system that utilizes external battery management system. The basic requirement here is that no electrical connection can bypass the BMS. If you bypass the BMS, it won't be able to detect these, for example, to shut down the loads or charging system. So we heard about a few stories when somebody tried to fast charge the batteries with external BMS and connected the battery charger that didn't meet the charging profile for the batteries, and basically overcharged the batteries. So that's why we require that nothing bypasses the BMS. Only the circuits that are designed by the manufacturer can do that. For example, you have all the circuitry designed for cell balancing. That's before BMS. And of course, the BMS, like all electrical equipment, it should have its own voltage rating, current rating. That's pretty straightforward. So what happens during the shutdown? As we said before, we have the safe operating envelope. If any of these limits go outside the safe operating envelope, the response from the BMS is the shutdown. So there are a few things to consider. It's not a requirement, but something to think about. Any critical systems like navigation equipment, for example, maybe it's a good idea to have the second power source in case if the BMS cuts off the power to these systems, and that alternative power source can be a second lithium-ion battery. It's not the requirement, but it's something worth to consider. Also, there is a recommendation that there is the visual or audible alarm before the BMS disconnects the battery. It's not a requirement, it's a recommendation. Not all the shutdowns are easy to predict. In case of overcharging and over discharging, it's a little bit easier because you can see that the voltage is raising, and it will reach the limit soon. Or but for example, in case of like external heat source, it might be difficult to predict. That's why we cannot require that alarm. Overcurrent protection. So basic E11 requirements would apply here. So there were a few confusions here because often BMS contained like an internal circuit breaker, but that circuit breaker is there just to protect the BMS and internal electronics of the battery. It's not intended to protect the conductor, because the battery manufacturer doesn't know what size of the conductor you have on the boat. Therefore, you need your regular overcurrent protection to protect the conductor, to protect the battery cables. The other things to consider here. Okay, battery switches. Often these batteries, that they will have like an internal switch or external switch, so that's the output disconnect device that's controlled by the BMS. But still there is the requirement for the battery switch, and that can be a manual battery switch, that can be remotely operated battery switch, but you still need to have the battery switch that's accessible and located as close as practicable to the battery. And we have that requirement that's readily accessible. So that basically means that's capable of being reached quickly and safely for effective use under emergency condition without the use of tools. And that's the definition that we use across all our standards. So yes, the battery switch is still required, even if the battery has its own disconnect device. Charging sources. Of course, the charging sources, they should have the charging profile designed for the battery. Again, follow the battery manufacturer's recommendations regarding the charging profile. Generally, most LFP batteries, they're actually very close when it comes to the charging voltage to your AGM batteries. What are potential problems with the charging sources is, for example, the load dump. So when the BMS disconnects the battery from the charging source, because the voltage got to the level when the BMS, the BMS disconnects everything, at least on the charging side, that can be potentially damaging to, for example, alternator or other electronic circuits. And that's not like a use problem, that's more like an installation problem. So that's something that needs to be figured out on the installation phase. And there are multiple ways to address that problem. It's pretty straightforward. You can use DC to DC converters, you can use battery isolators, you can use second, for example, lead-acid battery, and connect that with the isolator to your lithium-ion bank. So there are a few ways to address the load dump. The other is like that I think I mentioned about that the alternator overheating possibility, because the lithium-ion battery, unlike lead-acid battery, will accept very high charging current. It's not limited by its internal resistance as much. And what happens even when the alternator and engine is on idle, the charging current can be very high. while the cooling fan on the alternator, doesn't spin very fast, so it can cool that alternator sufficiently. Something to be considered when on the installation phase. There are different ways to address it. You can install the larger alternator that can supply that large current and be able to it's able to be cooled down. Or most likely what you can see on boats today, you can see alternators with external regulators and temperature sensors that can prevent overheating. Okay, so let's see, battery banks. Also, when you connect the lithium-ion batteries into the banks, so when you create either parallel or series connections, follow the manufacturer's recommendations, because the connecting the batteries can create either currents or voltages that exceeds the limits of the internal battery components. So often you have battery manufacturer requirement that you cannot connect more than, let's say, 4 batteries in series. So just double check the instruction from the battery manufacturer before building a battery bank. Okay, we can switch that. Okay, so we are getting close to our presentation here. I think I haven't exceeded my maybe a little bit exceeded my 45 minutes. And again, I encourage everybody to check our website and check all the events that we have, all the available resources, a lot of free resources on our website, free courses, online courses. In February, we'll have that Certec event. It's a 2-day online event. You can sign up for 1 or 2 days. Well, the day 1 is for the surveyors and day 2 for technicians. And we'll be also talking about lithium-ion batteries and DC systems, analysis, advanced electrical systems. And so if you're interested, you're welcome to sign up. Okay, since that's the end of the presentation, I'll stop sharing my screen and I'll take some water and see if we have any questions.
Thank you so much for a very informative presentation. So Priscilla, you're monitoring the chat room, correct?
Yes, and I had a question, or we had a question, but 2 of the participants, Kenneth and Paul, managed to connect and answer a question about their torpedo battery system. So do we need to go any further with that question, Kenneth? Was that answered to your satisfaction by Paul?
Paul, I'm not an expert, so I'd like to hear from the expert.
Yeah, so let's see, what was the question?
The question is, an NMC battery for Taquito, should it be charged at 80% or 20% left? And Paul gave it an answer that the rep told him about it to don't charge it to 100 during the storage, but when it's being used, then charge it to 100. Do you have anything to add that was specific to the Torpedo system?
I will definitely follow the what the Torpedo says about in their instructions. The general rule of thumb is, if you want to store your lithium-ion battery, their NMC or LFP, you don't want to charge it 100%. It won't affect the safety of the battery, but it will affect the lifespan, the longevity of the battery. So if you think that you are putting your boat in storage, just charge it like 70% and it should be fine.
Does that pertain to AGM batteries as well?
No, the AGM battery, that's the lead acid chemistry. So that's totally different.
So Ken, did that help with the with your question? I don't hear anything from Ken, so I guess maybe it did.
All right.
It sounded like he said it was saying it wasn't a storage question.
Right.
Let me see if I can find that question.
I couldn't find out how to turn off the mute. I got it now. Yeah, my question was not a storage question. It was a when do I charge the lithium-ion battery when it says it's 80% expended? And
oh, if you have to wait till it's all discharged. From what I know, no, you don't have to wait. You can charge it, anytime. And that these batteries are controlled by the BMS, so you cannot overcharge them.
It just seemed on your chart that it starts losing power at 80%.
Yes. The
Okay.
voltage, you can see the voltage dip when it's like a discharge around 80-90%. So when it's almost completely empty, then you can see that the voltage is going down.
Okay, and I have another question, which was, is it possible to charge a lithium-ion battery from a regular chemical battery, and if so, how?
Yes. So when you have, like, for example, two different batteries on the boat, like you have your lead acid battery and your lithium-ion battery.
Right.
Is that the question?
Yes.
Yes, you can do that. So there are devices that you allow to do that. Many brands they have this DC to DC chargers, or DC to DC converters. So they basically take and they're programmable. So they'll basically take one voltage, because voltage is two different batteries. So they'll take one voltage, and you can program that and convert to the voltage required for your lithium-ion battery. And the same thing, you can charge your your 24 volt bank from 12 volt bank using DC to DC converter. So that's totally possible.
An easy converter. Thank you.
DC to DC. So that's.
We have a question. Do you know if the Coast Guard has advanced any requirements for inspected vessels?
I haven't heard anything about that. So the Coast Guard is currently working on, actually they're working with ABYC on new guidelines. And as far as I know, they might just recommend using ABYC E13.
Okay, anything else coming up in the questions? I don't see anything. Does anyone have a question that they could open their microphone for?
You mentioned a website to go and find this information, possibly a copy of this presentation for further study. What's the website that you referred to?
So let me see. Let me see if I can show it on the screen. It's a ABYC website, so that's American Boat and Yacht Council, and I'll share the screen again to show everybody. Okay, so that's where you can go to our website, and you can find, maybe I'll do like a short overview, because you can find a lot of interesting stuff here. ABYCinc.org. I'll put that in the.
The website is also on the CAPCA members side. We have a link to ABYC. So if you didn't write it down, you can go to the member side of the CAPCA website at capca.net.
Yeah, I'll put it in the chat too. So
yeah, there it is. Magic.
And
so
the session will also appear on CAPCA's YouTube.
Yes, when the video is ready to go on CAPCA's YouTube, it will appear on the CAPCA website in the same place that the link for tonight's program appears. So you can find it initially, and otherwise it will be forever ensconced on CAPCA's website, the ABY, on our YouTube.
Yeah, so
We have one other question.
Uh-huh.
What about, well, we actually have two other questions. It's not.
Okay.
What about placing these batteries in the cabin? Is it safe? Do they give off gas?
No, I mean, yes, it's safe, and no, they don't emit any gas under normal operating conditions. That's the difference between the lead acid batteries that can vent hydrogen, and they require venting to get that hydrogen outside the boat because it's explosive. And the lithium-ion batteries, they do not emit any gases unless they go into the thermal runaway. So that's the situation that we want to prevent by having a BMS. So under normal operating conditions, there are no gases emitted by these batteries, and they are safe to install in the cabin, yes.
And the question that everybody probably wants to know, and if you've been following the trades, you'll have some answer. Do you expect to see more electric propulsion systems for boats in the next 5 years?
Yes.
Yes. They're
we
all
had,
over the place.
yes, they're all over the place. I was in Met Trades in Amsterdam, and you can see a lot of these new electric propulsion systems. You can see, and there are all kinds of systems. You can see like a low voltage systems, what we call, so below 60 volts, like 48 volt system, usually for the slower boats. And you can see the high voltage systems, like, for example, 800 volts DC for the high speed boats. So yes, we can see, yeah, we can expect more electric propulsion.
What about the availability of raw materials, lithium and so on, for production of batteries? How do you see that developing?
I would hope that the manufacturer they'll start recycling these batteries, because they'll end, eventually they will reach the end of their life after 10-15 years, so they can recycle lithium from the batteries, and I'd like to see that. I mean, it's not my not much I can do about that, but hopefully it will be economically viable for them to recycle these batteries. But yes, so the nice thing about lithium mining is one thing, but the nice thing about lithium iron phosphate batteries is they do not contain any cobalt or other heavy metals, so they are not considered toxic this way, and there is also no ethical problems with mining cobalt. Not all chemistries are like that, but the lithium iron phosphate is definitely, better.
And we have another question that we think about when we have cars, but this is for boats. What kind of charging input from marina electrical will be required for fast charge systems? Will 30 amp and 50 amp be enough to handle robust lithium systems?
For the fast charging, no. For regular charging, yes. So when we, think about the charging, we can have like an onboard charger, and if for the weekend sailor or the cruiser, that might be not a problem. They go to the marina, they plug in, they charge overnight, and that's fine. But there are a lot of these like power boats, wake boats, surf boats. It's not really my thing. I'm more, I'm a sailor, so. But there are these people that they want to go like to the fuel deck, go there,
Yeah.
plug in half an hour, and they're charged. And then your 50 amp, it won't be enough. there are fast chargers on the market and that they can do that, but that requires much more power from the grid and from the marina. And they're being installed, but yes, that's a totally different system.
Anything else?
Okay, then thank you so much, Maciej, for your very, very informative presentation. We will put it up on our YouTube channel, and I'm sure some of our members will also want to go to your site to get more information. And I hope all of you will join us next month when we have Captain Novak, who will be speaking to us about rogue waves. So it should be interesting to hear his personal experience as well as the science behind rogue waves. So if there is nothing else, we'll officially adjourn the meeting. And thank you all so much for attending and for your
Thank
presentation.
you.
Okay, thank you.